Thank you, Ben. Good morning, everyone. I'm very excited to be here at the fourth Automotive CFD workshop that is taking place in a UK university, just like as it started in 2019 at the University of Oxford. It brings me a lot of memories and flashbacks from my student life in the UK, so I'm very excited to be here. So today I'm here to talk to you about the overview of the mesh in TFG, and also I'm going to talk about the committee meshes that we generated using ANSA. Disclaimer here, you probably know already that beta is part of Cadence now. It's just that we didn't have the time to get the correct PowerPoint templates. We will be given in due time. So an overview of the mesh in TFG. This is the number of participants. So a wide distribution over different fields. So 26 individuals and 19 institutions. Of course, to be fair, I have to say that these are all the people that just registered, right? The actual participants, active participants, were a bit less, but still they were from all over software vendors, universities, OEMs, and consulting companies. The aim of the workshop was to establish a common understanding of the relevance of meshing factors and quantify their impact. Of course, this is a sentence that contains a lot of work, right? And I'm not here claiming that we did show the answers to all of these things. And of course, once we did this, we should come with the purpose of this workshop is to come with best practice for meshing that are applicable to industrial cases, right? This is the interest of the OEMs that are participating here. Some of the topics that were discussed over the meetings that were taking place every 5 weeks included, of course, how to create a mesh-independent solution, you know, features like the domain size, the mesh resolution, curvature refinement, wake refinement, layers, mesh type, polyhedral standard. And of course, if there's a unique answer for all the problems, right? Probably not. I also had in mind if it were possible to create some sort of universal mesh quality criteria, because one of the challenges of creating the committee mesh is to make everybody happy, and it's not easy because different CFD solvers have different, peculiarities, different calculation of, cell centers, phase centers, and it's not always easy to have everyone happy. Another important topic had to do also in couple with the noise TFG was mesh consistency, repeatability, depending on, the hardware, the actual geometry, and so on. We also did some additional work on, because the final meshes were polyhedral, in parallel to that, because some participants had solvers that used standard type meshes and high order meshes, we also generated some of these. Some points that were, some questions that again popped up in the meetings was if the committee mesh, which is an octave mesh, the fact that it has this jump of cell size 1 to 8 in volume, if it causes any issues to, hybrid run-cell simulations. Some people discussed if we could have a coarser mesh because there was only one mesh level refinement, which was concluded from previous workshop, but maybe that was a bit large in size. We wanted also to examine the effect of changing the resolution separately on the surface and the volume and see, which one was most important. There was also a discussion on if we could have a platform where we could exchange meshes so that we could exchange some know-how. And okay, after all these discussions, there were bottlenecks. One bottleneck I would say is that, generating meshes without solving them is useless. And it's always a matter of resources, right? So everybody can generate a mesh, but, somebody has to solve it and get some conclusions. Otherwise, it's not useful. And, everybody who has contributed actively in this workshop knows that this work is done in overtime in parallel to our everyday job. And in the end, we didn't conclude on such a platform where we could share meshes and exchange, know-how. So the actual TFG outcome, I would say, is that we generated new meshes, new committee meshes, for cases 2A and 2B after very useful participant feedback, especially Burkhardt's team. And also I would like to thank Miguel from Total Sim USA for his contribution. These were, as I said, octary meshes, hexadominant, highly suitable for hybrid runs. Based on the conclusions from previous workshops, we went only for wall function mesh because we saw that there was no actual benefit to spend extra resources, and we outputted 4 mesh formats. As I said, we also generated some meshes on standard element type and high order meshes for some of the participants, as you will see. We did a lot of work in parallel with Ford to do meshing noise studies, as you will see in a very interesting presentation afterwards. Multimatic made a very nice presentation on mesh adaptation. And also we have work that compares the committee meshes with custom meshes. This is very interesting because what we actually wanted as for our contribution was feedback. And feedback not only from OpenFOAM users, but from other users as well. Very briefly, we started in providing the committee meshes from the first automotive CFD workshop. Back then, we used the traditional standard meshing, triangular surface mesh, layer extrusion, and then filling up the volume. This, of course, created a buffer zone of some pyramids and tetras between, which could be converted to polyhedral. But still, in the second workshop, we decided that we should go for an octary mesh for various reasons. First of all, most OpenFOAM users prefer this kind of mesh because OpenFOAM was developed on such a mesh, like Snappy Hex Mesh. But also, the octary approach is more efficient. It's much easier parallelized so for speed up. And also in practice, the standard meshing approach requires a watertight surface. And even though the dry wire geometry is a representative automotive geometry, it is very far from the actual complexity of a real automotive case, right? And having a watertight surface is not as easy as one may think. Of course, one could use surface wrapping, but in my opinion, if you take the effort to set up an octary process that will generate a surface wrap, you might as well use it to create a whole volume mesh, right? So I think for automotive applications, the octary extreme approach is the best approach, and similar measures like that. Then for automotive CFD, AutoCFD4, we create a very similar mesh with the addition of the deflectors. And now we reached AutoCFD4, where in fact we created completely new meshes, updated, very similar to the ones before, but updated, after the feedback of our participants. These are some statistics, a wall function mesh, 7 layers, with around 157 million elements. The cell count was increased due to additional refinement, as I will show you. Some performance metrics, a meshing speed of 175 and 57 million cells per hour, and around 1 gigabyte of memory usage for a million cell. So the meshing approach starts from a tessellated geometry, where we define these so-called size boxes to refine the overall around area of the car. And here we can see a preview of the mesh refinement in a color plot. Then we add some additional sizing rules like surface offset or surface offset and sweep to refine the weight. And then we have a total size field that is distributed like that, where you can see the element length of every octary level. And this creates a very nice refinement zone. I would say we may have overdone it here, but just to be sure that nobody has any issues with that, we wanted to refine further the layers on the road. And this is the resulting volume mesh. As I said, the octary extreme meshing approach is a very efficient approach. And the most challenging thing of that is to be able to not sacrifice on quality, right? So we believe that our algorithm creates a very nice feature capturing. It resolves all the features without missing feature lines and curvatures and proximities. The variation of the element length on the car is, the maximum length is 8 millimeters in red, and it drops down to 0.25 near the contact patches. As for layer coverage, it's very robust. We generate 7 layers almost all around the vehicle. And the distribution of the total boundary layer height is around 12 millimeters. Some areas that you see it smaller is because the element length is so small that the layers do not want to inflate by more than the average element length in that area. The changes with respect to the automotive CFD2 mesh, it's very similar approach, just a few things that were changed. We increased the refinement around the wheels. We increased the refinement on the surface of the road. And we increased the refinement on some curvatures, like the ceiling of the rear window here. We wanted to capture the curvature in a much finer way to avoid any noise in the flow simulation. And you can see the effect on the volume mesh here. So you can see the increase in the refinement around the wheel and also on the layers near the wall. Another thing that is also important, as you will see in the following presentations, is that the original geometry had a closed plinth at the contact patch of the tire. For AutoCFD4, we opened it because, again, we wanted to make sure that we are as close to the experiment as possible. And regards to mesh quality, we believe that we have improved further the mesh quality of the mesh. Again, our target values are always open form quality criteria. So you can see that the maximum skewness is below the limit. It's around 3.5. And the orthogonality is just exactly at the limit of 70. And the growth rate is, very nice. There is a peak here in the 1/8 transitions, and the maximum is below 50, which should be okay. And we have done a lot of work in Extreme to ensure that we are very consistent every time we mesh a new geometry. And you can see here, for example, case 2A and case 2B, that when we add the deflector, you see nothing changes around apart from that local area, right? So the remaining mesh is exactly the same. With that, I would like to conclude and say that we would be very interested to have feedback from more participants on the committee meshes. As I said, we did our best always for open form quality, but even for other quality criteria. But although we had a lot of feedback from open form users, we didn't have feedback from non-open form users, and we would be interested in that. We have continued to make improvements in our algorithm. So now with the latest ANSA version 25, we have much better quality, and also we have dropped the total cell count, leading to smaller meshes that are faster to run. And I think we would like tomorrow in the afternoon, where we have the panel session, I think we should discuss again the meshing TFG objectives together with all of them. It was a very interesting experiment. I think it went very well for all TFGs, but we need to reconsider, what are the aims and what we can expect from a meshing TFG, right? Especially given the workload that everybody has. With that, I think I can have concluded. We can continue with the actual presentations. Thank you.